Good afternoon, students. Today we are going to discuss VLSI system design, unit 5. Okay, that is programmable logic devices. Okay, generally these are called, in short, PLDs. Right. So before going to start PLDs, let us see the basic concept. Okay, everyone knows ICs, right? What do you mean by IC? It is integrated circuits, right? Basically manufactured in a wafer. Okay, right. So the basic structure of ICs, let us see. Generally, the ICs will be designed in this fashion. Okay, depending on the functionality, we have number of pins. Okay, plus VCC, minus VCC, and input output depending on the functionalities. Right. So this is IC. Now, what is the use of basic IC? Okay, suppose uh, to apply a logic function, we use ICs which are available in the market. For example, I want to develop a logic function. Okay, suppose I want to develop a logic function, a very project, whatever it. Okay, in this I required, suppose, say mux or decoders, etc. Okay, then I can simply use ICs. ICs are which already a mux or whatever the functionality programmed and manufactured. Okay, so these ICs can be useful with a fixed functionalities which can be used in the whatever the requirement logic functions. Okay, we can use, right? So see, suppose while developing in our laboratories. Okay, so generally I want to use 3-4 ICs as of as per my function requirement, right? So what is the advantage and disadvantage of these ICs? Basically, these ICs are used in student laboratories, okay, not in the industries. Okay, these methods is practically not used in the industries. Why? Because see, I will give few drawbacks of these ICs. Okay, so let us see, I'm using n number of ICs for my logic circuit or logic function, then definitely using uh, more ICs, then the power consumption is more. Therefore, I can say large power is required. Large power requirement, I can say, right? And the second one is, see, in this case, generally ICs, the chip will be very small only, the IC, right? If you go through it, definitely the chip is very small, but the interconnections and pins, okay, which are makes more space, okay, taking more space. Therefore, what will happen by using n number of ICs in our logic function or a circuit which are developed by students are, okay, then what will happen? It will take more space. Okay, so I can say large space requirement also, large space requirement. And the third one, anyway, I'm using to develop n number of ICs individually, therefore the cost also increases. So I can say higher cost or large cost. Okay, so generally these methods is practically not used in the industries. Remember this. Okay, so it is not useful for long term designs. Okay, so basically these ICs are used in the laboratories, student laboratories, for practice purpose. Okay, then then designers introduces new concept or new technology called application specific ICs. Generally, in short, we will call ASICs. Okay. See here, this is a wonderful concept. ASICs. Suppose generally, uh, if you want to develop, suppose I want to develop adder, subtractor, etc. These logic circuits, then if I realize these adders with the help of logic gates, right? We will develop logic gates. Then what will ASICs do? ASICs will convert these logic gates into transistors. Okay, so transistors may be either FET or MOS. Okay, CMOS, whatever, right? So entire logic gates will be converted that, okay, into transistors level, okay, based, and they will design the circuit, okay, and manufacture, right? So what will happen, this type of ASICs will be take more process, okay. When it is useful means if we have bulk number of products produces, okay, it is useful only when the large number of products produces. For example, nowadays we have mobile, great, very higher industries mobile, right? Mobiles generally the processor contains Qualcomm or we can say Intel. Okay, these Intel or Qualcomm processors will developed by ASICs only, but it is n number. For example, 1 lakh, 2 lakhs at a time they will design that particular processor and produces n number of uh, what you can say processors. Then that will be useful. Otherwise, suppose for example, in our lab or we want to develop a single chip with the use of ASIC, then what will happen? All this entire process, whatever taking by converting general realization to ASIC, then what will happen? It will take more process. Then I can say simply, initial investment is very high. So I can say if I going with single or very small amount of products, then what will happen? Initial investment and is very high. So it is for low amount, I mean low productions, low number of productions, okay, design productions, ASICs are not recommendable because it contains very huge high cost, right? So when long term or number of products produced, okay, then it will be useful, right? Okay, we will see next PLDs. The ASICs contains PLDs programmable. When programmable concept, then it is comes under PLDs and FPGAs also. So we'll go with PLDs. So already we written PLD is nothing but programmable logic devices. What do you mean by programmable? Programmable is nothing but, see, initially the whatever the designed chip is empty. You can specify, you can give input output functionalities so that you have certain functional logic function, okay, logic circuit, whichever you want. Okay, it is not fixed one, right? So you can program after design, after manufactured, you can program particular device, whatever the functionality you required. Okay, so that is the major advantage. Okay, so let us see programmable logic device, right? So generally these are LIC, LI, sorry, LSI circuits. Generally, suppose if I write, generally these are LSI circuits. Okay, What do you mean LSI? Large scale integration. If we see the IC generations, so we have generally SSI. SSI means what? Small scale integration. MSI, medium scale integration. Then LSI, large scale integration. Then VLSI, very large scale integration. Then ULSI, that is ultra large scale integration. Okay, so these circuits PLDs comes under LSI. Okay, large scale integration, right? So generally, what are the components contains the PLDs? So PLDs generally consist of AND gates, OR gates, and buffers and inverters, flip-flops also if you require, right? So these basic gates, end or operation, SOP, right, as we know. Okay, so let us see the types of PLDs. What are the types we have, right? Let us see few more points about PLDs. Okay, generally PLDs implement two-level logic circuits that are AND and OR. Let us see this. This is implement two-level logic circuits that are what? AND and OR. Okay, and these are the simple logic arrays. Okay, so I can say simple logic arrays. Okay, and these are also not complicated one, based on a regular array structure. Okay, these are regular array structure. Okay, let us see the types of PLDs. What are the types we have, right? Okay, types of programmable logic devices. Okay, so we have the first one, read only memories. Okay, so basically that is programmable ROM, read only memory. Okay, and the second one is programmable logic array. It's nothing but PLA. Okay, and the third one, programmable array logic. That is nothing but PAL. Okay, so these are the various several types of PLDs basically. Okay, let us see the functionality. Here, just observe this slide, classification of three basic PLDs, these PLDs only, right? So here, see here, the first one, PROM, okay, programmable read-only memory. This is programmable read-only memory. See, here we have two-level programming, okay, two-level implementation of logic circuits we have, right? The first one is fixed AND gate. Okay, so that is a fixed AND here. Okay, so basically for a ROM, as we know, that is a decoder. Okay, next is programmable R. I can change programmable R plane, right? So R logic will be there. This is programmable. One is fixed. Okay, so anyway, the decoder is fixed, okay, whatever the type of decoder, 3 to 8, whatever the, okay, so it is fixed, but you can program here, you can modify your logic by using R logic, okay. Then output, this is called programmable read-only memory, PROM, right? So next one, here whenever you give an input to, see, AND and OR operation both are programmable, so you can modify whatever the logic you required in AND as well as OR plane also, okay. So this is nothing but PLA, programmable logic array. Remember, programmable logic array in two levels also programmable, we can program, right? So whatever the logic we required, we can program there, right? Next, here third one is PAL, right? Programmable array logic. In this, remember, end plane is, end logic will be programmable, we can program here whatever the modification we need, and R is fixed, okay. So further, if you want extensions, we have flip-flops, anything, okay. So this is the output. Remember, once again I would like to repeat, PROM is, decoder is fixed, that is end plane is fixed, and R is programmable, so you can modify whatever the logic you required, okay. Then next is PLA. PLA is both AND and OR logics, or circuits, okay, are programmable, okay. So here we can program both, right? Next is PAL, program array logic. In this, end plane or end logic will be programmable, which means what, whatever the requirement of my logic I can implement here, and R plane is fixed, okay. So this is the classification, I mean classifying three basic PLDs, okay, right. This is very important, you need to remember this, okay, right. So therefore, as you observed, see, after manufactured, after design completion, I can give my logic whatever my requirement, right? So that are the advantages of PLDs, okay. So you can program after manufactured, after completion of design, you can give your own design by using and R planes, okay, and R logic levels, right. Basically, simply, I would like to give another idea of PLD. PLD is basically, we have three types, that is SPLD, and we know that is CPLD and FPGS. FPGS, okay. So what are these three? SPLD is nothing but simple programmable logic devices. So I can write here better. FPLD is simple programmable logic devices, okay. Then what is the CPLD? As you know, this is complex programmable logic devices. Then FPGS, what is the FPGS? Field programmable gate arrays. Anyway, we are going to study further in this unit only, right? So a simple programmable logic device contains, what are the PAL, PLA, and PROM, okay, programmable read-only memory, okay. This is general structure. So extension of CPLA and FPGA I don't want to discuss here, okay. Whenever the concept comes, okay, we'll discuss there, right. So this is the basic idea of PLDs, right. So there are three types of PLDs basically, okay. Read-only memories, that is PROM only we are taking here, programmable ROM, not general ROM, MROM, okay. And programmable logic array, and programmable array logic, right? So we'll see the first one. We'll see the first one, read-only memory, PROM, programmable read-only memory. Okay, let us see read-only memory, ROM. Okay, the first one, PLD's first one, classification, read-only memory. Okay, so let us see what is this. What do you mean by read-only memory? Okay, so it is nothing but a memory, okay, stored in ROM, right? So generally it is called permanent binary information, okay, which can be stored in ROM, okay, but we cannot modify it simply, okay. So it is nothing but permanent binary information, okay. This is nothing but permanent binary information, okay. So one of the best advantages of ROM is, see, ROM can help us to implement combinational logic circuits, which is nothing but we can program ROM, okay. So when ROM is programmed, then it is called PROM, okay. So second one, if I say, so ROM helps us to implement a combinational circuit, okay, combination logic circuit, okay. So generally ROMs use it to help us to implement a program in ROM, okay. Therefore it is nothing but programmable programmable ROM, read only memory. Generally it is called PROM, okay. So PROM is nothing but programmable read only memory, okay. So if I define ROM is a memory device which can store permanent binary information and can be used to implement combinational logic circuit, okay, can be used to implement combinational logic circuits, okay. So let us see what are the basic advantages of ROM, okay. So we'll see the advantages, okay. Let us see few advantages of ROM, okay. So in ROM generally design is very easy, okay. So simply I can say easy design, okay. Simply I can say very easy to design. And the second one is design can be changed rapidly, very easily we can change the our design, okay. So design can be changed rapidly, okay. And the third one, so basically ROM is I can say LSI circuit, okay, large scale integration circuit, okay. So therefore these are faster than MSI circuits, okay. So these are faster than MSI circuits. PROM are faster than MSI circuits, okay. And therefore the last one, it is reduce the cost, okay. So these are the basic advantages of uh, ROM, okay. So that is an advantage, PROM, okay, programmable read only memory. Let us see few disadvantages or drawbacks, I can say, okay. See, for every circuit, suppose I designed one circuit, my logic, okay, function, okay. So here I written my design here, okay. I realized my design here. Then what will happen? Utilization of the circuit is non-utilization of the circuit, okay, is here. Okay, suppose I completed here up to here, then this complete circuit is not utilized. Okay, this is one of the drawbacks we have in ROM. Okay, so the first drawback is non-utilization of complete circuit. Okay, so non-utilization of the complete circuit. And second one is, see, so whenever this is a large number of components includes with the logic, these logics basically. Okay, so I can say simply there is large power consumption. Okay, so large power consumption, power is very large. And the third one is, if we increase number of inputs, for example, I increase number of inputs here, therefore the size of this circuit will be increases. Okay, then for the cost increases and the power increases. Okay, same vice versa, right? So if we increases, if we increases the number of inputs, then the size of generally the circuit will increases. Okay, so if we increase the number of inputs, then the size of the circuit will be, our logic will be, our functionality will be increases. Okay, so these are the few drawbacks we have, right? Then let us see ROM functionality or organization, I can say. Okay, so I can say simply read only member organization. Okay, how generally it is organized, right? Now let us see the ROM. This is basic ROM and consist of say for example, okay, these are address inputs. Okay, this is address input, and we have data output. Okay, so data output is nothing but in this case memory. Okay, so see for example, what is the relation between address and data output? Okay, in this ROM, see for example, data output is nothing but if I ask to read some book, okay, the page number for example 52 and second paragraph, okay, that is nothing but data output. Okay, so for that you required address of what, 52 page number. Got my point? I repeat once again. Suppose I ask one student to VLSI textbook page number 52 and second paragraph. Okay, what is that paragraph? Okay, for that the student is required address, that 52 page number is required. That is nothing but address input. Got my point? To represent the data output, see paragraph is nothing but data output. Okay, to know that one 52 page number is a address line. Okay, address input. Got my point? For example, if I take another example, okay, suppose I have a consultancy. Okay, if I want to meet my client, what I required? If I want to meet certain student, one student I want to meet, okay, so what I required is address I need to know, okay, then only I can access him, right? Simply. So the address specifies the memory location where the data is stored. Simply the address, otherwise I will write here better to note down. The address specifies the memory location where the data is stored. What point? Okay, what the point? Simply to access someone we need to know the address. Okay, that is the relationship between address input and data output. What my point? Right. Now this above representation only we can write internally how it will be. Okay, so let us see how it will be. So this is ROM. Okay, and we have rows like this. Okay, and the columns. Okay, now this is nothing but we can say address lines. Okay, so we can say memory location. Okay, so this is memory location, which is nothing but address. Okay, this is complete true, right? Now this will be represented as cells. Okay, and this entire rows and columns of particular cells will be taken as word. Okay, these are called words. Okay, so the data output related with words all the time. Okay, so this is, I can say, the data output. Okay, so in this fashion entire memories will be located in the cells. Okay, so this is the relationship between memory address inputs and data output. Okay, now let us see the functionality or organization of ROM. Okay, okay, right. Now I will redraw the diagram. What happening? Okay, we'll make it undo. Right. So let us draw this. Okay, this is ROM and consisting of address lines, address input like this. This is address input. Okay, so I am representing this as a K. Okay, and the data output I am representing this as a small n. Okay, so if K addresses, I can say address lines is equal to 2 to the power of K addresses. Okay, so ROM size generally will be considered as, what is that? 2 to the power of k into n. Remember this. Okay, so it is considered as 2 to the power of k into n. This is nothing but here 2 to the power of k into n. This is the size of the ROM. Okay, so if you understand better, let us take a small example. So consider a small example here. Suppose we have 32 into 8 ROM. Okay, then see 32 is equal to how much? 2 to the power of k, right? What is the k value here? Then it is comes 5. Okay, so therefore now what is means? Therefore 5 address inputs, okay, and 8 right here is the 8 data output. Okay, and number of bits and number of bits is equal to total how much? 2 to the power of k into n. 32 into 8, which is nothing but 256 bits. Okay, so this is a simple example of 32 into 8 ROM. Okay, so this is the sizes of the ROM generally we need to calculate. What my point? Okay, so let us take internal functionality of ROM, okay, by taking a simple examples. Okay, example. Okay, now consider a ROM. Okay, now I would like to take 8 into 4 ROM. Okay, let us see this one. So 8 is equal to 2 to the power of k. What is that k value now? K is equal to 3. This is nothing but address lines, or I can say address inputs. Okay, or input sequence simply, right? Now let us design PROM, okay, with 8 into 4 ROM, right? So make it up, right? So here is now we have 3 inputs, so therefore 3 address lines, 1, 2, 3. See, in the ROM, basically I want to tell one point here. We have data outputs, but we do not have data input in ROM or ROM. Why? It is only readable, not write operation. Okay, we don't have any write operation. Therefore, we don't have any data input. Address lines we have, but not data input. We have only data output. Please note this point. As we studied, as you are studied in the subsystem design ROM, I think, okay, you know that point, right? Suppose these values will be, I would like to take A2, A1, A0 is a address lines. Okay, then the output will be Y0, Y1, Y2, Y3, Y4, Y5, Y6, Y7. Okay, so therefore this one I'm drawing here. The connecting wires I'm taken with other color. This is 6 and the final one is 7. Okay, now this is, as we discussed, this is 3 into 8 decoder. Okay, so this is nothing but AND operation. In this case it is decoder. Okay, so this is fixed one. Okay, as per ROM, this is fixed operation, right? We can't program here. Okay, this is a fixed one, we cannot modify here, right? Now see, in this, what are the outputs? These are the OR operation we have. Okay, this is OR. Okay, here is OR, this is end operation is decoder here, in this case fixed. Now this is OR operation. Okay, so let us see the OR operation here. So this one I'm writing. How many outputs we have? Data, sorry, how many outputs we have? 18 to 4, right? So 4 OR gates required here. Okay, so this is one, and this is second one, and third one, and this is fourth one. Okay, now in this case, see here, one of the important point. Suppose if I intersect these two, right, this intersect these two, each intersector stores 1 bit information, which means if these two lines are connected, it's nothing but high here, that is logic 1. Okay, so I write here each intersector, this intersector, okay, intersector stores 1 bit information. Okay, which is nothing but generally if it is connected, if connection, then logic high, then no connection, sorry, no connection, then it is logic 0, considered as logic. If there is no connection, it is nothing but 0. Okay, if there is a connection between two interconnect, then automatically it is high. Okay, so for this one, let us see same example of 18 to 4 ROM. Okay, I am considering this example only here. Example, so I have a truth table. Okay, 3 input only, so 3 address lines, I can say input or address lines. Okay, so that are say A2, A1, A0. Okay, which is consisting like this. Okay, with the decimal values, 1, 2, 3, 4, 5, 6, 7. Okay, sorry, 0, I forgot 0. So initially we will write this one better. So let us write 0, 0, 0, 0, 1, 1, 1, 1. Okay, next is 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. This is, so decimal, if I can convert this binary into decimal one, 0, 1, 2, 3, 4, 5, 6, 7. Okay, now, okay, now, so I'm taking example of 4 into 8 ROM, sorry, 8 into 4 ROM. Okay, so 4 outputs we have, right? So let us consider these 4 outputs. I'm considering x3, x2, x1, x0. Okay, now you need to mention the your own functionality. This is programmable. Okay, so OR gate is this, what are the outputs here? It is programmable, right? So let us write your own functionality in this case. Okay, so what are they? For example, here 0, 1, 1, 0, 0, 1, 1, 0. Randomly I'm taking this one. Okay, so this is my functionality, what I required. Okay, this is my logic which I want my output, right? So example one I am taking here is 1 1. So for example 0 0 1 0 1 1. Okay, certain values. For example, say 0 0 0 1 1 1. Like this, I'm taking 0 1. Okay, or example, this is 1 1 0 1 1. Randomly, I'm taking here. Okay, you can take any value. This is my output. I require this output, right? Okay. Now for this one, we would like to write mean terms. Okay. So let us write the mean terms for this one. Okay. So I will move a little bit here. Right. So let us write the mean terms for this one. Okay. So x3. So x3 mean term is what? x3 1 2 high high 1 2. Next is 5 6. Okay. So 5 6. Okay. Now next is x2. So mean term is 0 1 is high, 0 1, then 1 4 4, then 6 7 4 6 7. Okay, like that you need to complete all mean terms. Next is 3 4 5 7 3 4 5 7. Okay, x0 x naught 0 1 both are high, mean terms 0 1 both are high, then 3 4 7 3 4 7. Okay, now completed. Okay, so go up for the same circuit, I mean same design. I took the same example only. Move up. Okay, here is the example, right? So these values I'm taking same as x0, x1, x2, x3. These are right. This is my output, 4 output, 18 to 4 RAM. Okay, so now let us give the connections. X3 is what? Connected with 1 2 5 6. So let us interconnect 1. We'll take with white better. 1 2 5 6 5 6. Okay. Now this x3 is completed. Now x2. X2 is what? 0 1 4 6 7 0 1 4 6 7 0 1. This is 0 here. It is connected. X mark is nothing but there is a connection between two wires. Okay, 0 1. What is that? 0 1 4 6 7 4 6 and 7. These are the interconnections. This is the output. Okay. Next x2 x1. X2 is completed. X1 is 3 4 5 7 3 4 5 7. Let us connect. This is 3 3 4 5 7. These are connections here, right? So last one, x0, the data output 0 1. What is that value? 0 1 3 4 7 0 1 3 4 7. Just remember that 0 1 0 1 3 4 and last one 7. Okay, so this is the functionality of internal functionality of RAM. Okay, so every output in this case is a mean term. Remember that. Okay, as you know, every output is data output is a mean term in this case. Okay, so this is one of the basic example of the RAM. Okay, internal functionality. Got my point? So let us see another example which is repeated in academic examinations. Okay, got my point? Right. So let us see another example. Example 2. Okay, so in this case I would like to take 8 into 6 ROM. Okay, let us presently I am taking basic examples, that is address lines will be 3 address lines. Okay, 8 means 3 only, right? So which is nothing but 8 is equal to 2 to the power of k. Now what is the value of k? K equal to 3. These are the address line, address inputs. Okay, now so in this case suppose question is asking he want square functionality. Okay, square functionality. Okay, the output I require functionality. Okay, so what output is I want a square output. Okay, for my design I want square output for a PROM. Okay, so let us see 3 inputs only, same, write the truth table. So this is A, B, C. In this case I'm taking A, B, C. Okay, let us we'll draw the, after this we will draw the design. Okay, A, B, C. Now sorry, okay, now if I take decimals, this one 0, 1, 2, 3, 4, 5, 6, 7. Okay, so values will be 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay, this I remember like this. Okay, now what are the outputs we have? How many outputs are now? So this is inputs up to now. Outputs will be 8 into 6, I said, right? 6 outputs. So generally it is called x5, x4, x3, x2, x1, x0. 6 outputs. Okay, 6 outputs in this case, right? So what I required in this case, question is asking I want my logic as decimal value, logic as square, right? So in this case I will write the decimal value as a square. Okay, square, right? So square means what? 0 square is how much? 0. 1 square is how much? 1. So right, 0 means what here? 0, 0, 0. So generally weight, the value code weight values will be 1, sorry, 2, 4, 8, 16, 30. This is the weightage, right? So 2 square is how much? 4. Okay, let us complete this one. 1 means what? This is what value, complete 0, 0, first one. Okay, second one, 1 means this is 1, remaining all terms will be 0. Okay, next is 2 square is how much? Input 2 square is 4. 4 means this is the value, this is high, remaining all will be 0. And 3 square is how much? 9. 9 means 1 high, sorry, 8 high and 1 high, remaining terms will be, digits will be 0, right? 4 square is a 16. 16 means this is high, remaining terms will be 0. Okay, like that you need to complete. 5 means 25 square, 25. So generally 25 means you need to take 16 high and 8 high. Okay, 16 high, 8 high, and this one 25, right? 24, 25, remaining terms will be zeros. Okay, then this is 36. 36 means what in this case? 32, 0, 0, 1, 4 is 36. Okay, next is 7, 49, 49 square. 7 square is 49, right? 49 means 32, 16 is 48, then 0, 0, 0, 1. Okay, now this is the function which I want is square. Okay, square output I require. I want to program square output at a R level. Okay, R logic, right? Anyway, end logic will be fixed in the ROM, PROM. Okay, now let us draw the design. So okay, so anyway, this is 3 into 8 decoder. Okay, it's nothing but end logic and decoder, this one, right? So how many inputs we have? 3 inputs. What are they? I named it ABC. Address lines, generally it is called address lines. A, B, C. Okay. Now this one initial will be 2, 1, I0, and this one will be Y0, Y1, Y2, Y3, Y4, Y5, Y6, Y7. Okay. Now for this one we have extend these lines, connecting wires. Third one, fourth, fifth, sixth, and 7. Okay. Now we need to develop the R logic. What is R logic? This is R here. Okay. So anyway, this is fixed in this case, decoder, and this is programmable in PROM. Okay, as we know, right? Now let us develop here R gates. How many outputs we have here? 6. So 6 R gates you need to write here. 1, sorry, 2, 3, 4, 5, and 6. Okay. So what are the values? What are the values here? X0, X1, X2, X3, X4, and X5. Now make a connections, okay, by seeing above when it is low, when it is high. Okay. Now X5. X5 means what? If you want, you can write min terms here in this case. Okay. So output data is always min terms, right? So shall we write this one? See here, X5 is 6, 7. Okay. X5 is 6, 7. So directly I am connecting here. Okay. Otherwise you can write min terms. X5 is equal to some min term is 6, 7. Okay. So it's nothing but with white 6, 7. Okay. Next X4 min term is X4, go above. X4 is what? 4, 5, 7. That's all. 4, 5, 7. 4, 5, 7. Okay. So therefore 4, 5, 7. Okay. Like this you need to connect all connections. Okay. As I discussed, okay, connection will be logic 1 and no connection will be 0, logic 0. Next, this one is next is this is what 3 3 5, that's all, 3 5. In this case, write min term x3 is equal to min term is 3 and 5. Okay, so it's nothing but, okay, wait for a few minutes. Three and 5, 3 and 5. Okay, sorry, that is x3, x3, x4 we written. Three and 5. Okay, it is not here. 3 and 5. Next is like that, you need to interconnect or logic. Okay, next x2. X2 is 2 6, 2 6. X2 is equal to min term 2 and 6. Therefore, x2 is equal to 2, x2, 2 and 6. Now, x1, see here, there is no connections to x1, no connections to x1. Okay, therefore, no connections. X naught is, this is 1 3 5 7, 1 3 5 7. Okay, x1 is equal to 1 3 5 7. Okay, sorry, this is 7, 1 3 5 7. So connect here, 1 3 5 alternative 7. Okay, so these are the data output of the PROM. Okay, so this is, I think you got, this is end is fixed, R is we are programming. In this case, what? Square functionality I took. Okay, so square functionality, this is my output. Whatever the input you will give, it will become a square now. Simple. Okay, okay, so this is another example, right?